Okay, good morning. The work that I'm going to present today was part of an activity that we carry out together with Dean Aswegen. And the target was to basically look at the effect of laser shock peening on one of the alloys that you typically use for airframe structure. All the work that was done before was on the Unclad version, but obviously for a lot of application, you actually have a layer of clad that usually protect the material, obviously from corrosion, but we want to see what kind of effects we have with laser shock peening. So the activity was done in collaboration with the Council for Scientific Industrial Research in South Africa, but also with IBAS Germany and University of Bologna. So obviously then we got sponsorship from a number of entities. This is just a brief outline of what I'm going to talk today. So let's skip to the processing. So as you know, Prof. Sano and other colleagues showed, there are different ways to do laser shock peening. The way we typically doing in South Africa is we're using a medium range commercial laser. And for this specific type of application, we work with a no coating. So we have no basically additional protection on the surface. In terms of confining medium, for this specific work, we work with the distilled water, but some other works, we actually work with the deionized water. So this is just a very, very, very simple schematic of the architecture of what we call it our research work cell. The other more expensive laser we're using for other industrial work. But basically, as I say, this is a quad-array laser. It works at 1064. And for this activity, obviously, we try to configure the system in such a way that we are not only processing the sample, but what is not shown in the picture, we have all a set of monitoring system to make 100% sure that the process is very robust in terms of, spot size and energy that we deliver. So there is, a lot of other toys that are included into the panel that are not shown in the picture. So first thing first, obviously we need to start to select some parameter, because obviously we have a range of parameters that we can use with the units that we have in the monitoring system online. So we decided to keep the spot at 1.5 millimeter, and thanks to the energy attenuator that we have, then we can change the energy without any problem up to 2.5 gigawatt per centimeter square. And also the coverage, so obviously how many spots we put per square millimeter, we can change within a certain range. The method that we use to select, let's say, promising parameter, it's based on a method that we kind of outline together with Dr. Glaser, that is basically a modified unmanned strip approach for shock peening, and very similar to what you have obviously for normal shock peening. We're trying to see at which set of parameters we have, let's say, an effective response of the material in terms of deformation. Beyond a certain point, we basically reach what we can call a saturation effect. So the type from the industrial point of view doesn't actually make sense going beyond that one, because we don't see many changes into the material. So the first thing that we want to look at is the damage that we basically cause into the surface. We have no coating. So obviously the laser is interacting directly with the surface of the material. And in the case of, as the picture that you have here for the Unclad material, we see obviously different aspects for the surface. We're working at a low coverage, so in this case 100, or in the pistol we're working on a higher coverage of 500. At the low coverage, what we see is that we had that this spot that is actually indicated by that blue circle is still quite obvious, so we can still spot the actual spot size, but there is an internal area that is not where the overlap basically doesn't happen, where we see some tiny feature that, apart obviously from the evident remelting of the surface, we have a little bit of cavity that are even more evident on the surface. When we're going into comparing what is happening at the different coverage for the Clad and Unclad, for the Clad version, maybe with this light is not super clear, but there was definitely much more evidence of plastic deformation on the surface. So probably because, again, the Clad is much softer material, is basically pure aluminum alloy. So mechanically speaking, it's something much, much softer. So in that specific case, In the case, well, I mean, in the case of Clad, obviously we're going to have much more plastic deformation. It was expected, but the other thing is that we also see a little bit less evidence of that melting effect, and maybe is due to the fact that the melting temperature of the Clad layer is just a tiny higher. The moment that we look in, what is happening on the surface at higher coverage, a lot of these features disappear. All these, let's say, bubbly effect on the surface disappear probably because we have increased working on the external surface, so more plastic deformation that is hiding that, and it basically disappear in the Clad layer. So there is obviously some mechanical effect that overcome the effect of the, let's say the thermal effect. In terms of surface roughness, we had a look at what happened on the surface. We had to go look in the two directions, what we call in the laser direction and the stepping direction, because we cover basically the surface with a rest and pattern. And we say that in both cases, we have a significant increase of the roughness, both for the Clad and for the Unclad sample. But what is interesting is that the Unclad, we're starting from a baseline of roughness that's a little bit lower, but after the processing, the roughness is actually higher than what we get with the Clad. So obviously there is some form of peak valley situation that is much more evident on the Unclad material. Here we're disappearing completely. So what we did, we cut, it's a cross section of the material. This is the base, the 2024, this is the layer of the Clad. So in the case of no laser shock peening, obviously there is no evidence on ablation of the surface. Here it's very difficult to see, I'm sorry, maybe the room is not dark enough, but with the laser shock peening, we actually see a visible ablation on the surface, and if we go in and actually measuring the thickness of the remaining Clad layer, we see that we are ablating about, let's say, 10 micrometer of material. So there is obviously some material that is partially removed from the surface. So in terms of hardness, obviously we're taking some, average measurement across the area where there is no laser shock peening and the area where there is laser shock peening. And in both cases, for the Clad and Unclad, we see a slight increase in hardness. So that's obviously that one from a certain point of view is good. It's not particularly evident, but in the Clad situation, the percentage increase in terms of roughness actually just a little bit higher than what we got for the layer material. So then the other things obviously we need to look at, it's the residual stress. What we were a little bit worried about is that this third layer might work as like a softening layer, and we actually not maybe able to transmit the full laser intensity in terms of deformation into the material. So we first ran two separate sessions of beam time at the Electra synchrotron in Trieste. And because of the synchrotron space, we can actually not fit samples that are bigger than a certain dimension. So with the logic of moving into more industrial type of application, the work was to starting to have some specific area that are processed with laser shock peening and to see basically what is the effect in terms of residual stress in the structure. So this sample is a little bit smaller. We have, let's say, a stripe of laser shock peening that we place in the middle, and we're starting to play with a certain parameter, but also with the position of the stripe, how wide is the stripe, how close is the edge. And obviously, again, I know that for a larger panel situation might change a little bit because the elastic constraint is changing, but we didn't have, this is the edge space that we have to work with. So moving forward, what we saw, we work at 3 energy levels. So we were able to go up to 120 micron inside the material. So obviously see a little bit on the surface and see what kind of residual stress distribution we have across the stripe of the material. Obviously, both in the case of Clad and Unclad situation. And in all cases, what we see, obviously, it's as expected that higher compressive residual stress in the middle of the stripe, but we also have that unwanted balancing tensile residual stress, that Domenico never wants, but there must be somewhere, otherwise these things flies away. Okay, so what we had to do, we obviously, as I say, play with different parameters, but we also had to do some single and double side processes. So in a lot of cases, we had to process the sample with one stripe only one side. But in cases to balance the deformation that otherwise you have in the panel, we have some double side. And that obviously we need to go and see what kind of residual stress distribution we have at the front and at the back. So coverage-wise, the more we increase in the coverage, the deeper and higher the compressive residual stress are expected. In terms of power intensity, obviously something similar. The more we increase in the power intensity, the higher the compressive residual stress that you have. So this is okay. What we're interesting to see what we have in terms of residual stress distribution in between the clad and unclad situation. So the unclad definitely has lower compressive residual stress at, obviously with the same type of parameter. But also a little bit wider distribution of the compressive residual stress field. Now, remember, these are we looking relatively close to the surface, so it's obviously not completely balanced. But there is also the fact that the clad is usually applied by core rolling. So obviously there might be an additional, there is actually an addition, maybe 50 megapascal that they come in from basically from the cladding process. And so obviously the distribution that we have are slightly different. The anointing is that we basically looking at a material that are actually two alloys together when we're working with clad, because we have the alloy of the clad, if you want, and the alloy of the base material. So we need to be careful that we're looking at the parameter with a double peak fitting function to making sure that we're actually looking at the proper residual stress that we have in one, basically in the clad layer and in the base material. This is very on the surface. We need to look what happened through the thickness. From an industrial point of view, we need to have a better picture of the thickness thing. So the first study we did in collaboration with the group of Prof. Fitzpatrick from Coventry, because the material is very thin, and there was a long discussion, and I won't drag you into this because the material is very thin. So to be under the standard for all drilling, there are adjustments that have to be made. So we did some of these tests with them, and we obviously see what now in a specific point, it's the residual stress distribution through the thickness, and make sure it makes sense because obviously we're starting to rebalance out through the thickness layer. After discussion, we basically came up with our own kind of type of approach. So we redid a lot of tests in-house for the different configuration with the MTS 3000 system from Seeing Technology. So that means now we can mix together the information that are coming from the synchrotron. They gave us basically a picture in the XY direction with the information through the depth that instead are coming from the whole drilling. So obviously we need to adjust the data in some way. Now, what the purpose of this is obviously going for fatigue testing and see what is happening. So now we're starting to talk about larger panel. That is the one that we're going to use. We put in the double stripe. We basically took the data that were coming from the synchrotron, and we try to basically distribute the residual stress on the surface. Obviously, there might be slight adjustment for that. The story is that now the panel to test it into a fatigue test machine has to be nice and straight. Okay? But because the more you process with laser shock peening, the more the panel is starting to deform. That's why we need to process this on the both sides. So after a number of trials, we basically come to basically straight panel. If we process in the back of the panel with basically 75% of the intensity, then it's basically straight. So the data in the XY direction, let's say in the Y direction, integrated with approximated with the Tada Paris. Data through the thickness, obviously we're going from high compression to tensile into the middle. We need to come up with an average because the software that we're going to use is giving us, we can only put basically one distribution. So we had to take an approximated average integrated residual stress distribution. So with that, what we have, that in this case, obviously the unclad and clad, they don't have exactly the same distribution. So the unclad looks a little bit more like this green curve, and the clad parameter instead are a little bit more lower on this side. So experimental test, we run it at the CSIR. So then we took this residual stress data, we put it into FGRO with the RTT method. Unfortunately, as I say, we can only put data into the Y direction. So we need that simplified distribution. And then we run the experimental test in the unclad version. then obviously to, adjust the data and see. And we got, nice, let's say, correlation. Obviously, there's a significant increase in fatigue life with the stripe. But what was interesting, obviously, if you're interested, there is a little bit more detail on that paper indicated there. When we had the model, and the model is decently benchmarked with experimental data, then we can play with the position of the stripe, the intensity of the stripe and the laser. So we investigated different things, and try to see obviously what is happening on the panel from the experimental point of view. So obviously, if you increase in change in the residual stress distribution, fatigue life is expected to increase. But we always need to be very careful, what is happening, because we always need to deal with that balancing tensile residual stress. So in terms of clad and unclad situation, okay, we see that in this case, it seems that the clad, it's obviously performing a little bit less than the situation that you obviously have with the clad Polese line. So yeah, done. Yeah, I'm done. So in synthesis, we have obviously we increasing the roughness and the micro hardness. We have compressive achieving the LSP region. But obviously, in both cases, we have a significant increase on fatigue life. That obviously that's what is important. What is obviously missing here is to see the long-term effect. So another work that obviously I don't have time to present today is to see, for example, the corrosion. So what is happening at the moment that you have modified surface and how it behaves that. So with that, I'm just closing. And if I can have 1 second more.
Okay.
Just that, in terms of, I'm here, but obviously I'm part of different type of consortium. So since this is the first time we're presenting at this conference, I just wanted to say that at the moment we are open for business, as we discussed it before with Arua. So if any of university, especially if you are within the guild, group, we have the possibility to have a lot of, let's say, relative significant amount of money for collaboration and PhD student. And we also part of this consortium from the African Laser Center. So everything that is linked to laser-based technology, we have a big, quite big European project at the moment with colleagues also from, let's say, Italy and Germany. So if you want to be part of that, that's my name. That's it.
Okay, thank you very much. You're very interesting presentation. We are over the time. Only one short question I can allow. Other questions? If not, then thank you very much again. Okay, other questions and discussion we can forward to the principal. I think this is yours. This is my.
Okay. Excellent. Now the next speaker will be Dr. Kasaev, Dr. Nikolai Kasaev. I have the pleasure to know him more than 1 decade. Excellent colleague, and he will give a talk on the identification of Johnson Cook material model parameters for laser shot peening process simulation. Dr. Kasaev, floor is yours.